Vaayusastra Future Scientist Meet, chapter number 51. The first presentation, Pulsar Planets, just done by team Target Space. Now, the second presentation is by our CEO of Aerospace Now, and he is going to present on this topic. So that's quantum behavior part 1. So I think Rakshan already presented few presentations on quantum physics. So I think this will be a advanced version of that. Rakshan, the stage is all yours.
Yeah, Jagu. Give me a minute, I'll share my
Yes.
screen. Give me a minute. Is my screen visible?
Yes.
Yeah. So, yeah, hello everyone. I'm Rakshansai Shivakumar, CEO of Aerospace Now. And today I'm going to make a presentation on quantum physics, chapter 1 and chapter 2. So, let's get going, shall we? So, we have 7 chapters in this research. And today we're going to see chapter 1 and chapter 2, introduction and particle physics alone. This presentation might be a bit difficult to understand for some of you. So if you don't understand, please reach out to me and I'll make sure that you guys understand it as much as possible. So let's get going. If you want to understand the universe, think of energy, frequency, and vibration. Do you know who said this? Anyone?
Nikola Tesla.
Perfect. You're awesome. This was said by Sir Nikola Tesla. Let's start. Chapter 1, introduction. So what we cover in chapter 1? What is quantum and its definition? Waves. Oops. Yes. Quantum entanglement. The Bell's theorem. The Schrödinger equation. Feynman diagrams. Quantum tunneling. And quantum tunneling in our lives. So we will see about this quantum entanglement and Schrödinger equation, quantum tunneling in upcoming chapters, but this will just be an overview and it will help you understand more in the upcoming chapters. Let's start. Quantum. So what is quantum? Quantum simply means amount. The word quantum means amount. I didn't type it here. I'm not going to just read what's given. I'll just explain it in my words. So quantum means amount, and this quantum physics is the study of subatomic particles and how they act, how they behave, and all those stuff. So the quantum, in the quantum state, there is a quantum state, and in quantum state, everything, every particle, every subatomic particle, everything is not like particle, but as waves. So I'll just show you. So in quantum state, we can show a particle like this instead of showing it with a nucleus surrounded by leptons, protons, and stuff. So this will be very simple for you to understand. I hope this will be very simple for you to understand. So what is quantum? Quantum is a state where any particle is defined as waves and not as particles. That's it. So the definition is, let's say a physical system, let's say an electron, and it has particular values which are unique to itself. And values, let's say attributes, which are given here. Values, attributes, these are unique to itself with its own unique energy. This is the definition of quantum. If this is extremely confusing for you, don't take it into mind. The second point will help you understand. So moving on to a very, very important topic, quantum entanglement. So quantum entanglement, let's say two subatomic particles or atoms, okay, they come together. We know that can anyone tell me what is the third law of motion? Can anyone? Newton's third law of motion.
Every
Vignesh?
action has an equal and opposite reaction.
Perfect, Darsh. So according to this, two particles or atoms, these come together and a force happens between them. I'll explain this later when I talk about Feynman diagrams. In this, both of them come together. Okay, we have two atoms, they come together and a force acts between them, which creates parity between both the atoms or the particles. Okay, let's say we have, how would I make this bigger? But anyways, yeah. We have two particles, yeah, they come together, they come near as possible, and there is a force acting. And these force creates an equal and an opposite reaction. So both of them get separated by millions and millions of light. But as I said, something called parity takes place between them. What does this parity do? So let's say an atom with two electrons. There are, I said two atoms, right? One with two electrons and one with three electrons, let's say. And the atom with two electrons, they both do not meet, okay? They both are separated by millions and millions of light years. And if there is a change in one atom, it will affect the paired other atom. This is entanglement, okay? So the word entanglement is just connection. So it's like the word entanglement was first used with spider webs for some reason. I don't know why. They were used for spider webs, but later entanglement became a part of quantum physics. So the link occurred in two atoms or two subatomic particles makes both of them related to each other, and a change in one affects the other, or a charge in one affects the other, no matter how long or how far they are. Okay. So this is supported by the Bell's theorem. Bell's theorem was in 1964. This is a very important date. You'll know why. So Bell's theorem states changes between atoms can be induced and occur instantaneously, even if the particles are very far apart. So until now, any doubts, feel free to ask, okay? I know this is going to be a very difficult topic. So any doubts, any doubts until now? Anyone? Okay, I take that as a no. So let's move on. The Bell's theorem. As I explained, this is the Bell's theorem. And this has a problem. So if both of them are separated, are very far apart, a connection or a communication between both the particles or atoms should be possible. And that communication should be instant, no matter how far they are. So let's say we know that the speed of light is 3 into 10 power 8 meters per second, which is 300 million meters per second. And if both of them are like 2 to 3 million light years away, and the information or the communication should be shared within like 1 second, the communication must be faster than light, right? So this creates a conflict with Albert Einstein. Who said in his general relativity, nothing can travel faster than light. So he disagreed with this quantum entanglement and Bell's theorem, and he said it as a spooky action at a distance. Who said it? Sir Albert Einstein. So moving on. Again, one of my favorites, the Schrödinger equation. Pronounce it like Schrödinger. G must be silent. Schrödinger. So this is the Schrödinger equation. Yeah, this might look very complicated, but yeah, this is pretty easy. What this shows is, I explained wave. Tell me if you can understand this, okay, anyone? So first of all these signs are wave functions, okay? I explained about wave functions in some of the previous slides, right? So wave function, first this bit says over time, the total energy evolved is equal to kinetic energy plus potential. Okay, all these symbols, where am I? Yeah, this, all these show wave function. This reverse 6 and T shows time. The total energy evolved over time is equal to, this is the kinetic energy of the wave function. Okay, everything in quantum physics is about wave function plus potential energy. So this V signifies velocity, and here it stands for potential energy. This again, the T square, this H is energy, square it, 2m. I'm not sure about that m, and this again shows wave function with time square and and time with x square. X is a variable of kinetic energy. So this is the Schrödinger equation. And anyone tell me if you are able to listen to this? Okay, I'm going to play a video. Anyone tell me if it's audible or not? Okay. Hello. Okay.
The Schrödinger equation
it? Is it audible?
Yes, Rakshan.
Okay. Okay. Oops, sorry.
The Schrödinger equation is the key equation in quantum physics that explains how particles in quantum physics behave. You want to know where your electron's going to go? That's the Schrödinger equation you'll need. So why does it look so complicated? Well, it's because in quantum physics, when you're describing what a thing like an electron will do, it doesn't follow the rules of particles, it follows the rules of waves. And that's what these psi's are, they're wave functions. Okay, so an electron is a wave, and a wave can evolve in space and in time. But it can't evolve in any old way. There are constraints about how it can evolve, and those constraints, that's what the Schrödinger equation is telling us. It says that over time, that's this bit, the total energy has to stay the same. And this total energy is made of the kinetic energy, that's this bit, and the potential energy, that's that bit. An example for a potential energy for an electron is just being in an atom. So if you want to see what a quantum object will do in the future, you need to find the wave function that will satisfy all of these bits of the Schrödinger equation.
So are you able to understand? Anyone?
I guess so.
Yes. Okay. Yeah. So I'll move on. Okay. So if you did not understand quantum entanglement, this might help. The Feynman diagrams. Feynman diagram, this is an example of Feynman diagram. This is so complicated, so just leave it. I'm going to draw a Feynman diagram. So before that, let's see a video, shall we?
Feynman diagrams are very useful because they take the complicated and abstract mathematics of particle interactions and show the equations as simple pictures of what happens when subatomic particles interact. The axes of Feynman diagrams are space and time, and the different particles get different lines. A photon is a wiggle, the gluons are spirals, the W and Z bosons and the Higgs
model, I'll explain it in the next chapter. The particle physics, I'm gonna continue that. So I'll explain it in just a few minutes. Please wait.
boson get a dotted line, and the fermions get straight lines with arrows. These arrows point forwards in time for matter particles and backwards in time for antimatter particles, and the arrows always flow from one side of the diagram to the other. The building blocks of Feynman diagrams are vertices, which are a joining point between three particles. The orientation of these vertices changes the story they're telling. This one shows an electron changing momentum when it emits a photon. But if we rotate it, it shows an electron and positron annihilation into a photon. You can build most Feynman diagrams from this set of vertices, like this.
So a Feynman diagram actually it shows entanglement and relationship between subatomic particles. That's it. Okay. And yeah. So let's say we have an electron. Okay. We have two electrons and both of them come together. Both of them move closer to each other, but they're not touching, but they're not too close. Okay? They just come close to each other and negative charges repel. We know that. So as this repulsion takes place, a weak force acts between them. This is a force, okay? This is not a box, this is a force. This force acts between the particles, causing repulsion. Every action is an equivalent and an opposite reaction. So an electron thus changes, an E minus changes into E plus, causing positrons. So both the E minus change into E plus, and if they were E plus, they will change to E minus. And negative, so this is Feynman diagram. What happens is, so now I'll explain quantum entanglement and you will be able to understand it a lot. Before that, I'll just move my virtual background for some reason. Yeah. So let's say, maybe you can see my video. We have two atoms, two subatomic particles, and both of them come close to each other. So not so close, okay? They just come so close. And the repulsion, the weak force takes place between them. So what happens is both the electrons, they get paired or they get entangled. So both of them get entangled and move apart. They keep moving apart for millions and millions and millions of light years. And even though they get entangled, even though they move away, they are still entangled. And this is everything that the Feynman diagram is. So able to understand Feynman diagrams? Anyone? Anyone doubts?
I have a doubt. Like,
Yeah, Vignesh.
like we were saying for neutronic particles, okay, like electronic particles, can you see what this repulsion acts in neutronic particles or not? This
You asked
Feynman.
whether this repulsion acts on neutrons, neutronic particles?
Yeah.
Okay. So
Yeah.
this repulsion actually happens in everything, but except neutronic particles. Why?
Oh.
Neutrons do not have charges. So what happens is they get tunneled.
Okay. Okay. So which gives instead of weak force, which gives higher force? Like between two particles, when we add electrons and proton, when we add two particles, do we get high force or weak force? Like,
okay. So I don't think you know this. That's why I asked this question. There are only 4 forces acting in the quantum field. Okay, gravitation, electromagnetic, strong, weak. Okay?
I know that.
Okay, you know that. So what's your question then?
My question is that using all of the forces, use only 3 matters like proton, electron, neutron. Proton, electron, neutron. So these 3 matters perform on these 4 things as you told. So I'm asking, so here is the weak force. Like weak force means that between two electronic particles you are saying. I'm asking, when we replace instead of electron, when we put proton, how many distance does it cover than this electron?
Okay, see, your question is, if we replace the electrons with protons, will there be weak force or any other force, right?
Yeah.
Okay. In all or most of the subatomic particles only weak force. Okay, because their weak force has less radius, more than saying range, has a less range, short range. Okay.
So what is the range of the weak force? Like because in our company we have going a research for that only. I'm asking, what is the radius of the weak force? I want the radius. Yeah.
You mean range?
Yeah, range.
Oh, that's okay. Weak force has a range of like 10 to the power 26 or 27. I'm not sure. Okay. 26 or 27 meters. this is the weak force. Weak force is range. This is what you're asking, right? 10 to the power 27.
Yeah.
That means 1 and 27, 26 zeros. 1,
Yeah.
0, 0, 0, 0, 0, 0, 26 zeros. Yeah. Any other question, Vignesh?
That means like I'm asking planet to planet distance. It's the distance between Earth to Mars or Earth to Moon. What is the distance?
Average distance Earth to Moon.
Okay.
Okay.
Rakshan, actually, I'm pretty confused. 20 to the power 26 is way greater. It's like such a big number. How can it be the distance between
Is
Earth
it
and
minus 26? 10 power minus 26.
What is it, Jagu?
It's 10 power minus 26. No?
Yeah.
oh, minus?
So 0.000 26 zeros, then
1. Then 1.
yeah. So it's like very, very minute. And
So anyone
I
else?
don't know whether it's possible to replace electrons with protons.
It actually happens, Jagu. It actually happened. So not electron. I just gave electron as an example because everyone might know it. But actually, Feynman diagrams are explained with photons and positrons, not electrons.
Yeah,
I just
photons and
derived a
positrons are fine. Electrons and protons
Photons.
are yeah.
No,
Ah.
not photon.
Okay.
Photon, PHOTON.
So
Photon.
both have same diameter range, right? Both have
Both which two?
proton and electronic particles. Both of them.
Yeah.
Okay.
Cherry,
and
I think you can continue, Rakshan.
No, yeah. Okay, yeah, I'll continue. So moving on, quantum tunneling, a very important phenomena that happens in our life every day and we're not noticing it. I'll explain how. So, yeah. So quantum tunneling, I'm just going to tell you a story, okay? A small short story of quantum tunneling. So imagine you're on a highway, okay? Chennai to Bangalore highway or maybe, and you're driving at the speed of like 200 and 300 kilometers per hour. If you have a very expensive car. So you're driving at the speed of 300 kilometers per hour. And suddenly there is a turning. And in the turning, you come across a huge lorry or a huge bus or something. So what will you do? You'll just navigate around the bus with your control. But you're moving at 300 kilometers per hour, you're going to crash. Instead of that, something happens. You move right through the bus and come out of it like ghosts. Yeah. So this is the phenomenon of quantum tunneling. Okay. Yeah. This is the phenomenon of quantum tunneling. When one particle moves through another particle or an obstacle or anything. Okay. Yeah. So this is another thing. So think of it. In normal world, there is some what? Yeah, the point. And in the normal world, if you're rolling a ball, and there is a barrier, it just flows above the barrier and comes out. But what happens is in quantum physics, it just moves right through the barrier. This is quantum tunneling. So as I said, in the quantum state, everything is wave. Everything is a wave. And in a normal world, if you might not know, energy will always be greater than velocity and speed. So energy will be greater than velocity. And it always is like that. Normal world, quantum world, everything. Energy will be greater than velocity. So what happens is, while moving normally like this, when an obstacle comes in the middle, energy stays the same, but velocity increases rapidly, increases so much that energy cannot cope up with it. So velocity increases, energy is the same, energy is lesser than velocity. While it is through the obstacle, the energy will be lesser than the velocity. After that, it just comes back to normal. But there'll be just one change. A change in the height of the wave function. So let's say a wave function has an amplitude of 2 inches or something. 2 inches, I'm just saying, okay, it'll be like very small, but let's say it's 2 inches, yeah. And now after it went through the barrier or obstacle, it just reduced to half an inch. Why? This created, moving through the barrier, created an increase in velocity, and this made a huge problem. This problem changed the wave function. Rather than saying it's a problem, let's use a better word. Okay, this caused a change. So this change caused the wave function to reduce to like half an inch. So what happens was the speed of the electron or the particle moving increases with velocity, and the energy applied stays the same. So let's say I have a coin here and I just roll it, okay, and I roll it with normal speed. It passes with a speed of 5 kilometers per hour. When it gets quantum tunneled, if I push it with a and if it gets quantum tunneled and comes out, the speed changes from 5 to 100 kilometers per hour. The speed of the particle increases. So this is what I'm trying to say. Don't take it seriously. I just gave it an example of 5 and 100. So
just like again explain or understanding this.
You don't understand what? Quantum tunneling or what I explained there with a coin? Darsh?
No, that car going inside.
Okay.
Tree part.
Okay. Yeah. So you're driving, okay? You're driving in your car and you have a truck coming in front of you, okay? What you do is you just move around left or right and go right. So here in the quantum state, you go right through the truck, through it and come out. Okay, this is what I was trying to explain. You get it?
Not quite yet. Like
Okay, how it happens. So basically, all the barriers which are made of atoms.
Hello?
Yeah, hello.
yeah.
So
just
the
asking, like,
quantum
how it
particles,
happens.
yeah. For example, sound waves can travel faster in the medium than air. Okay, because in air the particles are loosely packed, but in solid it's tightly packed, so the sound can travel faster. So I think the quantum molecules also use a similar kind of idea. That when a barrier
it
comes,
will be able to circle. It can pass right through it. Okay.
Okay, so like using like how sound wave goes over.
Yeah, that's what. Yeah, you're right. The sound wave. Let's take sound wave as an example. Sound wave through air, sound wave to liquid, sound wave to solids. There is a change between them, and that is what I was trying to explain. Quantum tunneling.
Not 100% exactly, but the similar.
Yeah, that's more or less.
Yes.
Someone is annotated.
Yeah. Continue.
Date annotation.
We have 10 minutes.
So anyway, moving on to another. What I said was quantum tunneling is a very important part of our life, which we are not. Without quantum tunneling, we cannot actually live, because sun is getting the particles in sun are getting quantum. Deuterium makes up the hydrogen atoms. The hydrogen's proton and electron. I think you guys know it. Hydrogen has 1 proton and 1 electron, and these things are deuterium. Deuterium has the same composition as hydrogen, and is of we can say that deuterium makes up hydrogen in some way. So rather than having a neutron, it has deuterium. That's it. So two deuteriums in the sun gets quantum tunneled through each other. One second. I'm sorry. Two deuteriums in the sun get quantum tunneled through each other, thus forming hydrogen atoms into helium atoms. So two hydrogen atoms collide into each other, go in through each other, forming helium atoms. So this is quantum tunneling. And without this, how does the fusion process take place? Hydrogen and helium are the main parts of the fusion process in the sun, and without fusion process, no light, no heat, nothing. So deuterium and quantum tunneling are some of the most important phenomena in our solar system, which most of them don't know. Actually, I knew it only when I was doing this research study. So this is the end of chapter 1, and moving on to chapter 2. So chapter 2 will be like a lot more confusing than chapter 1. So Jagu, can we reconnect? What do you think?
Or you want to do it next week, chapter 2? I think we can close it with this week with chapter 1. We can
What is
continue
it?
next week. We can close this week with chapter 1. We can
Okay,
continue.
but I have a quiz with both chapter 1 and chapter 2.
That's okay. Anyway, quizzes are going to be after we disconnect and connect.
It's okay, Jagu. We'll just disconnect and I'll finish chapter 2 as soon as possible. What do you think?
It will be a proper live but
Whatever. Yeah. So okay, I understand. Understand. Yeah.
Okay, for what I do, I'll disconnect now. I'll put chapter 1 quantum physics. Then,
Okay.
We reconnect it. And anyway, we try recording the chapter 2 if it finishes
Jagu,
on time.
and again, என்னோட chapter 1 எனக்கு வந்து ரெக்கார்டிங் சென்ட் பண்ண முடியுமா?
Yeah. Yes.
Okay, எனக்கு சென்ட் பண்ணிருங்க. வாட்ஸ்அப் பண்ணுங்க, இல்லனா எனக்கு வந்து